Hello and welcome to this video for CE 108 Mechanics of Deformable Solids. We are still in chapter 3. We're talking about the mechanical properties of materials. In the previous video, we defined the concept of strain, and then we saw how stress is related to strain based on the Hooke's law. And based on this, we defined two key characteristics of materials which define how stiff they are, how resistant to elastic deformation they are, which is the Young's modulus, which captures how resistant a given material is to elastic deformation, and the shear modulus, which characterizes how a given material is resistant to shear elastic deformation. So now we're going to talk about a third elastic property of a given materials, just like the shear modulus and the Young's modulus. Now we're going to talk about another property, which is the Poisson's ratio. So before we talk about the Poisson's ratio, let's define some directions that are relevant to members when they are subjected to some loads. And so, for example, let's take two examples of loads. So let's take the example of a beam like this that is subjected to an actual normal load like this, where the load is orthogonal to the surface over which it is applied. And let's take the example of not a normal load, but now a shear load, where, for example, you have a beam like this, and this beam is subjected to a shear deformation like this, for example. And so this beam in this case is going to be subjected to a shear deformation, where in this time the load is applied along the direction over which over the surface over which it is applied. So in this case, in the case of a normal load, the load is orthogonal to the surface over which it is applied, and in the case of a shear load, the load is along the surface over which it is applied. So now in this case, there is some useful direction that are useful to define. So the first thing is this direction here, which is the direction of the length of the beam, which is also, in the case of a normal load, the direction over which the load is applied. So in this case, this is the longitudinal direction. This is the direction over which you have the longitudinal length of the beam. In the case of a shear load, this is the same thing. This would be the longitudinal direction. In the case of a shear deformation, the load is orthogonal to the longitudinal direction of the beam. So that is the first relevant direction. And then you have another relevant direction, which is the lateral direction. The lateral direction is the direction along the width of the beam. So this is the lateral direction. In this case, in the case of a normal load, the normal load is orthogonal to the lateral direction. So same thing, this would be, in this case, the lateral direction. In the case of a shear load, the shear load is applied along the lateral direction. So now the key aspect, so again, the key definition is that the longitudinal direction is the direction that is proportional, that is orthogonal to the surface over which the load is applied. It's if this is in this case, the surface over which the load applied, the longitudinal direction is orthogonal to this surface. So the longitudinal direction is the direction that is orthogonal to the surface over which the load is applied. Okay, so the load is applied. Okay, and so just to make it clear, the lateral direction is the direction that is parallel to the direction that is parallel to the surface over which the load is applied. And this definition is true both for the case of a normal load or shear load. the longitudinal direction is always orthogonal to the surface over which the load is applied, and the lateral direction is the direction that is parallel to the surface over which the load is applied. And again, this definition works both for the normal load or for the shear load. In this case, the lateral direction is orthogonal, is parallel to the surface, and the longitudinal direction is orthogonal to the surface over which the load, whether it's a normal load or a shear load, it's orthogonal to the direction of the surface over which the load is applied. So we are going to use those two types of direction, the longitudinal direction and the lateral direction, to define the Poisson's ratio. So again, the Poisson's ratio is defined based on some observation. And in this case, the general observation that is behind the Poisson's ratio is the Poisson's effect, which describes a typical behavior of a material. And in this case, the typical behavior of a given material that is called the Poisson's ratio is that if you have a beam like this, so this would be the beam before any deformation. So this is the beam before any deformation is applied. And then, so if we apply to this beam a normal stress like this, so we apply a tensile normal stress to this beam, so this will tend to elongate the beam. And typically what we observe in this case after the deformation is that this beam is going to be elongated along its longitudinal direction. But the other thing that is also going to occur is that on the lateral direction, if you elongate the beam along the longitudinal direction, along the lateral direction, the beam is actually going to shrink, so that after the deformation, the beam will look like this. So in this case, this would be what the beam would look like after the deformation. So, and this is the Poisson effect. It's the fact that when you tend to elongate a material along its longitudinal direction, it tends to shrink laterally. While on the other hand, if you compress a material along its longitudinal direction, it will tend to expand laterally. And the reason for this is that the material wants to keep its volume constant as much as possible. So if you elongate it along one direction, it will tend to shrink laterally to compensate the elongation. While on the other hand, if you compress a material along its longitudinal direction, if you have a given material like this and now you compress it, so you apply a compressive stress, then the material will shrink along the longitudinal direction, but will also expand laterally. So you will have a lateral expansion like this, while you have a lateral shrinkage when you tend to elongate the material longitudinally. So just to make it clear, in this case, this is the longitudinal direction, and you have in this case, the lateral direction like this. So in other words, if you have a longitudinal elongation, you will tend to have a lateral compression, and vice versa. If you have a longitudinal compression, then you will tend to have a lateral expansion. This is because the beam again tries to keep its volume as constant as possible. So again, so now it means that during the elongation of a metal, if you apply a given normal stress, for example, you will have two types of strain. You will have two types of deformation. The first one will be the one along the longitudinal axis. So along the longitudinal direction, longitudinal, okay. So along this longitudinal direction, so you will have one types of strain, which is that along this longitudinal, you will have a longitudinal strain. And again, so the way to define this strain is by looking at the change of the length. So you look at the length before the deformation L naught, then you look at the length after the deformation L naught. You can define the elongation as, so the strain after the elongation would be just L, so that's the length after the deformation. Then based on this, you define the elongation as the difference between the new length and the old length, and based on this, you define the longitudinal strain as either the new length minus the old length divided by initial length, or the elongation divided by the initial length. That is the strain along the longitudinal direction. That is the strain we have seen already. But now we see that in addition to that, there is also a lateral strain. So in addition of seeing this longitudinal strain, because of the Poisson's effect, because of the fact that when you tend to elongate something along the longitudinal direction, it will tend to shrink along the lateral direction. Now we have an additional strain, which is the lateral strain. And so this lateral strain, if we want to define it, we can define it in the same way. So we can look at the difference between the initial lateral length L of the beam and its new length. So let's call the initial length L naught for consistency, and the new length is going to be L. Then we can define a new elongation, which this one is going to be the lateral deformation. So this one was the longitudinal direction. So this one was delta, the longitudinal direction. Now we can define delta prime, which is the lateral deformation with the same definition. It's going to be the new lateral length L minus the former initial lateral length L naught. And in this case, you can also, based on this, define the lateral strain as the change in the lateral dimension delta prime divided by the initial lateral initial length of the material. So you applied exactly the same definition to define the strain. It's the change in the dimension divided by the initial dimension. And based on this, you can define both the longitudinal strain, which characterize the longitudinal relative expansion of the beam, and the lateral strain, which characterize the relative lateral deformation of the beam along the lateral direction. And in this case, what the Poisson's principle tell you, so this is again based on some observation, the Poisson's principle tells you, and this is not something that is proven, it's something that is observed, is that both the lateral and the longitudinal deformation are proportional to each other. So the lateral and longitudinal deformation are proportional to each other. Again, this is another manifestation of the fact that in nature, very often the cause is proportional to the consequence, or the consequence is proportional to the cause. So in this case, the lateral and the longitudinal deformation are proportional to each other. So again, so we can write this into an equation. And so what we can write based on this is that the lateral deformation is going to be proportional to the longitudinal deformation. We need a proportionality constant, and this proportionality constant, we are going to write it nu, where nu is going to be the Poisson's ratio. But here, if you look at in more details about what happens, every time you elongate a material along the longitudinal direction, then it's going to shrink laterally. While when you compress a material along its longitudinal direction, it's going to elongate laterally, which means that when you have a positive longitudinal strain, then you will necessarily have a negative lateral strain, and vice versa. When you have a negative longitudinal strain, then you will have a positive lateral strain, which means that in this case, the sign of the lateral strain is always, for 99% of the materials, opposite to the sign of the longitudinal strain. So since the sign of the lateral strain is different, opposite to the sign of the longitudinal strain, we're going to add a minus sign here so that the proportionality constant that we define nu is, in this case, positive. So this is, in this case, the Poisson's principle. It defines the Poisson's ratio, nu, which in this case, nu, which characterize the relationship between the longitudinal expansion, the longitudinal deformation of a materials and its associated lateral deformation. So this is what defines the Poisson's ratio. And again, in many cases, the Poisson's ratio is going to be positive because the sign of the lateral deformation is always opposite to the sign of the longitudinal deformation. So another way to rewrite this expression is that, so since we have the fact that the lateral strain, the lateral normal strain is equal to minus times the Poisson's ratio times the longitudinal strain, you can rewrite this to say that the Poisson's ratio is equal to minus times the ratio of the lateral strain divided by the longitudinal strain, which is another way to define the Poisson's ratio, which is fully equivalent to the equation on the top. Now let's look at the units. So in this case, since the longitudinal deformation, so that is in this case the longitudinal deformation, the longitudinal strain, the strain along the longitudinal direction, and the units of this longitudinal strain, no unit, it's a meter divided by meter. Then you have the lateral strain, epsilon lat, this is the lateral normal strain. Same thing, this quantity does not have any unit. And then the quantity that we just defined is nu, which is the Poisson's ratio. And in this case, since both the lateral deformation, the lateral strain and the longitudinal strain do not have any unit, then necessarily the Poisson's ratio nu also has no unit. Now let's look a little bit more detail at the sign convention again, just to make sure we are on the same page. So again, there can be two cases here. So if you have an initial beam like this, and then you apply a positive normal stress, then this will be the case where you have a longitudinal elongation. So the longitudinal strain will be positive. You will have an elongation along the longitudinal direction. And in this case, because it's elongated along the longitudinal direction, one way for the beam to try to keep its volume as constant as possible is going to have a lateral shrinkage. So you will have a shrinkage along the lateral direction, so that in this case, since epsilon lat is negative and epsilon long is positive, you take a minus sign. That means that the Poisson's ratio is going to be positive. And the other case is the case where now you have an initial beam like this, and this time you compress it. So because you compress it, you will have, in this case, the fact that the longitudinal strain is going to be negative. You will have a shrinkage in the direction of the longitudinal direction. And you will have, in this case, for the volume to try to remain constant. Like the volume is not constant, but still the beam tries to keep its volume as constant as possible. So if you shrink it longitudinally, then it's going to expand laterally. So you will have an elongation along the lateral deformation. And in this case, again, since the sign of the lateral strain is opposite to the sign of the longitudinal strain, then that is going to give you at the end a positive Poisson's ratio. So the Poisson's ratio of material is most of the time positive, but again, there might be a few exotic materials, especially metamaterials, that may have sometimes a negative Poisson's ratio, but 99% of the materials do have a positive Poisson's ratio. So now let's look at some typical values for the Poisson's ratio. So for most of the material, the Poisson's ratio is going to be between 0 and 0.5. Those are the limit, the upper limit and the higher limit of the Poisson's ratio. And in this case, a few examples is that, so for steel, the Poisson's ratio of steel is about 0.3. The Poisson's ratio of concrete would be about 0.2. The Poisson's ratio of glass depends on the type of glass, but around 0.25. And last example, Poisson's ratio of rubber would be about 0.5, where 0.5 is the upper limit. This is the maximum possible value, theoretically speaking, of the Poisson's ratio. This is the maximum theoretical value that the Poisson's ratio can have. So again, so the Poisson's ratio is, it characterizes the fact that if you try to elongate the metal in one direction, it's going to shrink in the other direction, and vice versa. So just try to keep in mind this definition. So it's very common for students sometimes to switch those two types of strain, like to say that the Poisson's ratio would be the longitudinal strain divided by the lateral strain. So just try to keep in mind and think about what it means. If you have a material like rubber with a very high Poisson's ratio, then a material like rubber, when you expand it, it shrinks laterally a lot. So for a given longitudinal deformation, the resulting lateral deformation will be very large. And this is because for rubber, the Poisson's ratio is very large. So try to keep in mind that large Poisson's ratio means large lateral deformation. So that the Poisson's ratio should be proportional to the lateral deformation, not inversely proportional to the lateral deformation. So that's one way to keep in mind or to memorize the fact that Poisson's ratio is minus the lateral strain divided by the longitudinal strain and not vice versa. In this case, unlike other expression, it's not possible to memorize this equation just based on the dimensions, since the Poisson's ratio does not have any unit, and the normal strain do not have any unit as well. So you cannot find the right expression based on the sign. Unlike the Hooke's law, for example, if you have sigma equal E times epsilon, then you know necessarily that you cannot have epsilon equal E times sigma, because in this case the units would not match. So in this case you can memorize this expression thanks to the units. But in this case, since there is no units, you have to memorize it based on your physical intuition that large Poisson's ratio means large lateral deformation for a given longitudinal deformation. So far we have defined 3 types of elastic properties that describe different types of elastic behaviors of materials. The Young's modulus, which characterizes the elastic resistance to normal deformation, the shear modulus, which characterizes the resistance to shear deformation, and the Poisson's ratio, which describes the Poisson effect, that if you elongate in one direction, it's going to shrink in the other, and vice versa. So one thing is that all those three elastic properties are not independent from each other. They are related to each other. So especially in the case of materials that are isotropic and homogeneous, you have a general relationship that relates those three elastic properties. So the general relationship in this case, it's only valid in isotropic and homogeneous materials, so materials for which the properties both do not depend on the direction and also do not depend on the position. Then in this case, the knowledge of two of those three properties, so the knowledge of two elastic properties, is enough to fully characterize the materials in terms of its elastic properties. So the knowledge of two properties, so for example, the knowledge of both the Young's modulus and the shear modulus, or the knowledge of the shear modulus and the Poisson's ratio, or shear modulus and Poisson's ratio, the knowledge of just two of those properties, of two of those elastic constants, is enough to fully characterize the elastic resistance of the materials, to the elastic behavior of the material. So it's enough to fully characterize the elastic behavior of the material. So what does it mean? It means that if you know two of those elastic constants, so let's say again the Young's modulus and the Poisson's ratio, for example, then you can calculate the remaining one. You can calculate the shear modulus. And in this case, the general relationship, again, that is only valid for isotropic homogeneous material, is that the shear modulus G is equal to the Young's modulus divided by 2 times 1 plus nu. So this is the general relationship for those materials that relates those three elastic metrics. And so in this case, it means that if you know the Young's modulus and the Poisson's ratio, then you can calculate the shear modulus, and vice versa. For example, if you know the shear modulus and the Young's modulus, then you can calculate the Poisson's ratio. So if you know two of those elastic properties, then you can calculate the remaining one. But just again, keep in mind that this relationship is only valid for isotropic and homogeneous materials. So this is all we are going to see in this chapter about the mechanical properties of materials. Those relationships that we have established here in terms of the Hooke's law, both in terms of normal and shear deformation, those are the relationships that we will keep using throughout the course of this material, because those are the key relationship that relates the cause of the deformation, that is the stress, and the consequence, which is the deformation. This is the Hooke's law. So every time you want to link some cause of the deformation to the resulting deformation, we will need somehow to refer to this Hooke's law. So those are the relations that we will keep using throughout the course of this class. So then in the following chapter, we are going to start to review different types of deformation, shear, torsion, bending, etc. And we are going to start specifically next week with the most simple case, which is the case of the actual deformation, the actual load. What happens to a material that is subjected to an actual load, how to calculate its elongation, and what types of stress that develops in those types of material. That is what we are going to see in the chapter next week.